Okay, our review of Chapter 16 here. Chapter 16 is our beginning of the study into electric charge and the electric field. Remember, we started with the fundamental rule. We call it fundamental because we don't know why this is true, but we see Mother Nature behave this way, and that is that opposites attract and likes repel. And when we're talking about opposites and likes, what are we talking about? Well, we're talking about electrons and protons, which are the building blocks of all matter. So charges, which are electrons and protons, are found within the atoms. The protons are found within the nucleus of the atom, and the electrons are found orbiting outside of the nucleus. The symbol for charge is the symbol Q, and you can either use a lowercase q to indicate charge or an uppercase Q. Q has units of coulombs, which is a new unit for us in the metric system, and we'll abbreviate it capital C. So there's a couple different atoms or / molecules that we want to take a look at. One of them is a polar molecule. A polar molecule is a molecule that when it forms has a permanent charge separation between the positive and negative charges found within the molecule. An example of a polar molecule is the water molecule. Water molecule is 2 hydrogens and 1 oxygen. So here's a picture of how it forms. So there's a large oxygen atom that attracts 2 hydrogen atoms in such a way it's at an angle of about 120 degrees such that the oxygen, having 6 electrons in its outer shell and wanting to satisfy the octet rule, will pull down the 2 electrons that each hydrogen atom has, so that there's an excess of electrons around the nucleus of the oxygen, leaving a deficiency of electrons or excess positive charge in between the 2 hydrogen atoms. So there's this permanent charge separation when the water molecule forms. Another type of atom is the ion. The ion is an imbalance of electrons and protons found within the atom. So if I take a neutrally balanced atom and I strip an electron away, then I have more positive charge than I have negative charge, and I would have a positive ion. If instead I push an electron into an originally neutral atom, then we would have more negative charge than positive charge, and that would be a negative ion. Lastly, an isotope. An isotope has different numbers of neutrons within the nucleus, and of course that does not affect charge at all, as neutrons are completely neutral in charge. A few different types of materials we want to consider. There are insulative materials, or insulators. These are materials in which the electrons are bound to the parent atom. So if you look microscopically at this material, you would be able to see exactly which atom belongs to which electron, and vice versa. Conductors are a different class of materials in which there are a sea of free electrons. So when you look microscopically at a conductor, you can't tell which electron belongs to which atom, as there are just a sea of free electrons. Semiconductors are materials like silicone or germanium that are doped with other atoms, and when we do this, it allows for us to control the material as either a conductor or an insulator based on how we apply a potential difference across the material. So semiconductors can act as switches, and they are found within many, in fact most, if not all, of the electronic devices that you own. There are 3 ways to charge an object: to either add an imbalance of electrons or take away electrons from a material. So the first way is to charge by contact. Charging by contact is just physically touching a charged object to an uncharged object. If these are conductive materials, then some of the charge will transfer from the charged object to the originally uncharged object, leaving you now with a charged object. So one way is to charge by contact. The second way is to charge by friction. This is physically rubbing the electrons from one material onto another material. An example of this is when you rub your feet across a carpeted floor. You're scuffing electrons off of the carpet onto your self, and when you walk across the room and touch, for example, a metal doorknob, you can see that buildup of charge that you gained by scuffing your feet across the floor transferred to the doorknob in the form of a spark. Another place to see it is on a dry day when you comb your hair. You are physically pulling electrons off of your hair onto the comb, leaving a deficiency of electrons or an overall positive charge on your hair. Like charges repel, and so your hair puffs up to get away from one another. To alleviate this, and it's more predominant on a dry day, to alleviate this you would use, for example, conditioner on your hair, and that would allow for less friction between the comb and your hair, thus less charge being transferred when you comb your hair. The third example is charge by induction. So if we start off with two metal spheres on insulating stands, as you see here, in physical contact with one another, they're both neutral. The electrons within each material, if these two are physically touching, don't really see two individual surfaces. They just see one big piece of metal that they're free to move around. If you bring a negatively charged object in the presence of these two spheres that are conducting, the electrons that are along this side right here will be repelled by this negatively charged object, again back to the fundamental rule. So those negative charges will move further away as far as possible from this negatively charged object. That'll leave a deficiency of electrons or an overall positive charge right here close to the negatively charged object. If you keep the negatively charged object in the presence of these two balls and separate them, then you have now two charged objects. Notice that nothing charged touched either of these objects. It just simply induced a separation of charge, and then you remove the physical contact between the two objects, and now you have two charged objects. Now we want to study Coulomb's law. Coulomb's law was formed by Charles Coulomb, who derived it and did a lot of work in the study of electrostatics from 1736 to 1806. If you consider two charges, Q1 and Q2, that are separated by some distance r, as this picture shows, the magnitude of the force one exerts on two is of course equal to in magnitude to the force two exerts back on one. They're a Newton's third law pair. And those magnitudes are given by Coulomb's law, which is the product of K, which we will get to in a second, it's just a constant, times the product of the charges. Notice the absolute value bars around the charges, because this Coulomb's law just gives you the magnitude, divided by r squared, where r is the distance between the two charges. So this is an inverse square law. The force, the magnitude of the force, depends inversely on the distance between the charges squared. K is a collection of fundamental constants and is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. If I was to place Q1 right here at r equals 0 and move Q2 along this axis further and further away, the force being exerted by 1 on 2 and 2 on 1 falls off as 1 on r squared. So it starts off infinitely large as the two are very, very, very close to one another, and falls off very quickly as they move away from one another. Coulomb's law only allows for calculation of the magnitude part of the force exerted by one charged particle on another. We know force is a vector, thus we also need the direction part. The direction part must come from the fundamental rule. There's only two ways that charge 1 can exert its force on charge 2. It will either pull charge 2 toward it if they're opposite charges, or it will push it away if they're like charges. So those are the only two directions, and the fundamental rule will tell you which of those directions it is depending on what the signs of the charges are. So you need both Coulomb's law and the fundamental rule to fully define the force exerted by one charged particle on another. So if Q1 is greater than 0 and Q2 is greater than 0, then we have a repulsive interaction between the two charges. They repel one another. So here's Q1 and Q2. You can see the force on 1 by 2 is such that 1 is being pushed away from 2, and the force on 2 by 1 is such that 2 is being pushed away from 1. The magnitude again comes from Coulomb's law, K, product of the charges involved with the absolute value bars around them, divided by the distance squared. And if the forces would point in the exact same directions if we had chose both those charges to have the same sign but both negative again. So either both positive or both negative, we get exactly the same picture with the forces repelling or pushing away from each charge and also the magnitudes given by the same amount. So we can fully quantify the force on charge 1 by charge 2 as k q1 q2 absolute value bars divided by r squared to the left, or minus x hat. F21, the force on 2 by 1, k product of the charges q1 q2 absolute value divided by the distance between them squared to the right, or in the x hat direction. Take the opposite scenario if q1's less than 0 and q2 is greater than 0, or if q1 is greater than 0 and q2 is less than 0, then we have an attractive situation. So it doesn't matter which is positive and which is negative, it just is important that they do have opposite signs. Then we have an attractive situation. So here again we have q1 and q2 separated by some distance r. Now the force exerted on 1 by 2 is to pull 1 toward 2. The force exerted on 2 by 1 is to pull 2 toward 1. The magnitudes are given exactly the same, Coulomb's law, k, product of the charges involved with the absolute value bars divided by the distance between them squared. So we can fully quantify the force on 1 by 2 as k, product of the charges, absolute value, divided by the distance between them squared, now to the right. And the force on 2 by 1 is equal to Coulomb's law k, product of the charges involved, q1, q2, divided by the distance between them squared, to the left. Now, if we have several charges, then we must vectorially add all of the forces exerted by each charge on a particular charge to find the net force on that charge. So, for example, if I want to find the net force on charge 1, well, charge 1 is feeling a force exerted by charge 2, but charge 1 is also feeling a force exerted by charge 3. All charges electrically interact with one another. So if I want the net force on 1, I need to individually figure out what force is being exerted by 2, both magnitude and direction, and then figure out what force is being exerted by 3 on 1, magnitude and direction, and then I need to vectorially add those two forces. So in this particular picture, I have assumed that q1 is greater than 0, q2 is greater than 0, and q3 is greater than 0. So q1 is feeling a repulsive force from q2, so that is to push it directly away from q2. Q1 is also feeling a repulsive force from Q3, so that means Q1 is getting pushed directly away from Q3. So the force on 1 by 2 is pointing in the first quadrant, the force on 1 by 3 is pointing in the second quadrant. So if I want to find both the magnitude and direction, I use Coulomb's law to find the magnitude part of each of these forces, or the length of these arrows. So the length of F12 is given by Coulomb's law k, product of Q1, Q2 absolute value bars, divided by the distance between 1 and 2, R1, 2, as is in this diagram, squared, and that's directly away from Q2. F13's magnitude and direction is given by the magnitude part Coulomb's law, k, product of the charges involved, Q1 and Q3 in this interaction, absolute value bars, divided by the distance between 1 and 3 squared, R1, 3 is in this diagram, and directly away from Q3. And then you would do the normal thing, find a coordinate system, project your forces along the coordinate axes, add x's to x's and y's to y's, the normal vectorial addition that we've been accustomed to since the first semester. All right, electric fields. Electric fields surround every charged particle, and in reality it's really this field that a charge exudes that's interacting with other charged particles near it. So what do these electric fields look like? Well, here's the electric field surrounding a positive charge. So here's a positive charge, Q, And you can see the electric field lines are radially outward. So they point radially outward. The spacing between the field lines is indicative of the strength of the field. So you can see as we move further and further away from this charge, the electric field line is getting smaller and smaller because the field lines are becoming further and further spaced. The electric field surrounding a negatively charged particle looks the same, except for you flip the direction of the arrows. So the electric field line points in on negative charges, points away from positive charges. The electric field is a vector, gets the symbol E. We put an arrow on top of it indicating it is a vector, so it has a magnitude and a direction. For a point charge, the electric field is given by K, the same value of K from Coulomb's law, times the absolute value of the charge that is exuding that electric field, divided by the distance you are from that charge, squared. The direction part of the electric field for a point charge is directly outward from the charge if the charge is positive, and directly into the charge if the charge is negative. There's only one of two directions it can be. So let's go ahead and look at the units that we're going to get for the electric field. So the units for the electric field are going to be the units for K, as was defined previously in Coulomb's law. Those units are Newton meters squared per Coulomb squared, times the units for charge, which is a Coulomb, divided by the units for distance squared, which is meters squared. 1 unit of coulombs cancels in the denominator with the one in the numerator. The meters squared cancels in the numerator and denominator, and we're left with a Newton per coulomb. So the unit for the electric field is a Newton per coulomb. So let's see what the electric field lines look like around a dipole. A dipole is constructed by having two charges that are attractive. So that means they have opposite sign. Either the one on the left is positive and the one on the right is negative, or the one on the left is negative and the one on the right is positive. All that will do is change the direction of the arrows, though. And the charges must have the same magnitude to be defined as a dipole. So these two charges have exactly the same magnitude, and you can see electric field lines emanate from the positive and they terminate on the negative. So the electric field lines look like this. Okay, emanate from positive, terminate on negative. What if you have two like charges near one another? Well, you have divergent field lines because the charges repel one another, and electric field lines can never cross. If electric field lines crossed, at that point in space, the electric field would not be well defined, and the theory would have real problems. So the electric field lines will never cross. These field lines diverge from one another. And you'd have exactly the same picture if you had two negative charges. You'd just flip the directions of the arrows. In general, if a charged particle, little q, is in an external electric field E, it feels a force given by the equation F equals QE. This equation will always hold. If you know the electric field at some point in space and you want to place a charge little q there, then you will know exactly what the force on it is by multiplying the charge by the electric field at that point. This is a vector equation and you do need to include the sign for q here. Very important. So what that tells us is that negatively charged particles will feel forces opposite to the direction of the electric field lines. Positive charges will feel forces in the same direction as the electric field lines. If there exists lots of charges in one area, we must vectorially add all the charges' electric fields to find the total electric field at one point in space. So let's take three charges, Q1, Q2, and Q3, that are located in this space right here. And we want to find what is the electric field right here at some point P. I just randomly picked a point. Well, let's assume that Q1 is greater than 0, Q2 is greater than 0, and Q3 is greater than 0. If they're all positive, then remember the electric field points directly away from the charge if it's positive. So E1 points directly away from Q1 because it is a positive charge. So here's Q1, here's E1 at point P. E2 will also point away from Q2. So here's Q2 at point P, E2 points directly away, again because it's a positive charge. E3 points away from Q3, same reason, it's a positive charge, so E3 will point directly away from Q3. The magnitudes of E1, E2, and E3 are given by the equation for the electric field's magnitude due to a point charge. So K, magnitude of the charge, which is Q1 in this case, so the magnitude of E1, K, Q1 absolute value divided by the distance from 1 squared. So the distance from 1 to point P is this distance R1 right here. The magnitude of E2 is given by K, magnitude of Q2 divided by the distance from Q2 squared. So point P is a distance R2 from Q2. And lastly, the magnitude of E3 given by K, magnitude of Q3 divided by the distance from Q3 to point P squared. And I'm indicating that as R3 here in this diagram. Once I have these three vectors, magnitudes, and directions, again, I just vectorially add them, picking a coordinate system, projecting any of these electric fields that aren't lying along my coordinate axes into component pieces, and then adding x's to x's and y's to y's, as we have been doing since the first semester. What do uniform electric fields look like? So far we haven't seen any uniform electric fields. We can create uniform electric fields by taking two plates and placing opposite charge on those two plates. So I've got a total charge plus Q on this left plate, and I've got a total charge negative Q on this right plate. You can see the electric field lines, they emanate from positive and terminate on negative. The spacing between these field lines is uniform, as you can see in this diagram that I've drawn, and that indicates that the electric field is uniform. So this is a place where we can see uniform electric field. If we're in an electrostatic situation, that means there aren't any charges moving around, then the electric field inside of a conductor is zero. Why? Well, if it wasn't zero, then the equation F equals QE that we were introduced to a few moments ago would tell us that if E isn't zero, then there's going to be forces exerted on charged particles within the conductor. Therefore, these forces would cause these charges to move, and it wouldn't be a static situation. In an electrostatic situation, any excess charge on the conductor is going to reside on the surface of the conductor, not within the volume of the material, but on the surface. And lastly, electric field lines in an electrostatic situation are always perpendicular to the surface of the conductor. If they were not perpendicular to the surface of the conductor, then there would be a component of the electric field that would be along the surface of the conductor. So if, for example, the electric field looked like that, then there would be a piece of the electric field that would be along the surface of the conductor. And again, the equation F equals QE would mean that there would be forces exerted on the charged particles within this material, because now we have a component of the electric field pushing along the surface. It's an electrostatic situation, so we never have electric fields that are along the surface. The electric field for a conductor is always going to be perpendicular to the surface. Okay, I hope that was helpful.